There is a version of this moment in which the universe is structured entirely differently, in which the atoms inside a single star collapsed one way rather than another billions of years ago, and the chain of consequences that followed led somewhere else altogether. And according to one of the most seriously considered theories in modern physics, that version doesn't merely exist as a thought experiment. It exists fully, physically, right now alongside this one, separated by something far stranger than distance. This is the many worlds interpretation of quantum mechanics. And to understand why physicists entertain something so audacious, it helps to start with the problem it was built to solve. Quantum mechanics, as a mathematical framework, works extraordinarily well. Its predictions match experimental results with a precision that no other scientific theory has ever matched. And yet, buried inside that framework is something deeply unsettling, something that has bothered physicists since the theory's earliest days. Particles at the quantum scale, before they are observed or measured, do not have definite properties. An electron doesn't have a precise location. A photon doesn't have a fixed polarization. Instead, these particles exist in what's called a superposition, a kind of smeared-out combination of all possible states simultaneously. The math describes it clearly. Reality, at its smallest scales, is fundamentally probabilistic. But here's where the strangeness becomes acute. The moment a measurement takes place, the moment a detector clicks or a photon hits a screen, the superposition vanishes. The particle suddenly has one definite value. The probability wave, as physicists call it, collapses. The question that has haunted the field for nearly a century is, what actually causes that collapse? What happens, physically, in that moment? Most people who learn a little quantum mechanics are given the Copenhagen interpretation as the default answer, which essentially says the wave function collapses upon observation, and asking what's happening before that point is meaningless. The math gives you probabilities. Measurement gives you outcomes. The rest is silence. For many working physicists, that was enough. It was practical. It let them calculate. But in the 1950s, a Princeton graduate student named Hugh Everett III found that answer philosophically unbearable. He looked at the equations and asked a question that sounds almost too simple. What if the wave function never collapses at all? What if all the possible outcomes actually happen? What Everett proposed was that when a quantum measurement takes place, the universe doesn't pick one result and discard the others. Instead, reality itself branches. Every possible outcome occurs, each in its own separate, equally real branch of the universe. The electron detected on the left side of the screen? That happens. The electron detected on the right? That also happens. In a different branch, a different world, a different continuation of reality that diverges from this one at precisely that moment. And the branching is relentless. Every quantum event, every radioactive decay, every photon absorbed or reflected, every particle interaction anywhere in the cosmos, produces a fork. Two paths, where before there was one. Then each of those paths forks again, and again. The tree of worlds grows at an almost incomprehensible rate, constantly, everywhere, from the Big Bang to this very second. The number of branches that have already accumulated since the universe began is so astronomically large that no analogy really captures it. Every star, every molecule, every heartbeat involves quantum processes. The branching is not occasional. The branching is the texture of reality, which raises a question worth sitting with. If all these other worlds exist, why can't anyone see them? Why does any observer only ever experience one outcome? Everett's answer lies in something called decoherence. When a quantum system interacts with its environment, with air molecules, photons, surrounding matter, the delicate quantum interference between its possible states gets scrambled almost instantly. The different branches stop being able to affect each other. They become, for all practical purposes, separate and non-communicating. Each branch evolves forward in total isolation from the others. The observers inside each branch have no access to what's happening elsewhere, because the branches can no longer interfere. Every version of every observer experiences exactly one outcome, perfectly consistently, with no awareness of the others. Because awareness itself is a physical process, and physical processes decohere along with everything else. This is where many worlds becomes philosophically vertiginous. Every possible path actually takes place. The road doesn't just branch, and then one branch disappears. Both branches persist. Both evolve. Both contain observers who are equally real, equally convinced that their branch is the only one. The distinction between what happened and what could have happened dissolves completely. Every could have happened did happen, just somewhere else in the structure of reality. Consider what that means for something as simple as radioactive decay. A radioactive atom has a fixed probability of decaying within a given window of time. In the many worlds picture, it both decays and doesn't decay, in separate branches. If that atom's decay would have triggered a detector, the detector both fires and stays silent. If that detector's output influenced any subsequent event, a choice, a signal, a chain reaction, then every downstream consequence also branches. The implications scale upward without limit, and they scale all the way to human life. Every decision the brain makes involves electrochemical processes that, at their root, are quantum mechanical. The argument can be made, carefully, with appropriate humility about the complexity of neuroscience, that the branching reaches into the fabric of thought itself. Somewhere in the structure of the many worlds tree, every choice that seemed close was also made the other way. Every possibility that felt genuinely open was genuinely realized. Everett's theory was largely ignored in his lifetime. He published, received little recognition, left academia, and died in 1982, never knowing that his interpretation would eventually become one of the most actively debated frameworks in the foundations of physics. Today, it has serious defenders, including physicists who argue that many worlds is the cleanest, most mathematically natural reading of the quantum formalism, one that adds nothing beyond what the equations themselves demand. The objections are real, and serious physicists raise them. The question of probability is particularly thorny. If all outcomes occur, what does it mean to say one outcome was more probable than another? Work continues on this, with approaches like Everett's own relative state formalism and later developments using decision theory and what's called the Born rule. The debate is alive, unresolved, and conducted at the highest levels of theoretical physics. But the core idea stands as a genuine contender for how reality is structured. Every possible path actually takes place. The universe doesn't choose, it branches. And what any single observer experiences as a choice, as a random outcome, as a quantum event resolving one way rather than another, that is simply the local experience of one thread in a vast and permanently ramifying structure. There is something almost vertiginous about sitting with this long enough to feel its weight. Every quantum event of this kind creates a split. Every split creates more. The tree of worlds is not a metaphor. In the many worlds picture, it is the literal architecture of existence. And this branch, this thread, this particular sequence of outcomes, stretching back through every coin flip of physics since the beginning of time, this is only one of them. Uncountably many others are equally real, equally ongoing, each inhabited by versions of every observer who will never know the others exist. The universe, it turns out, may be far less interested in making choices than anyone assumed. It may simply be in the business of containing all of them.